Hi class, this video is walking through how to do a one sample t-test in SPSS. So we've walked through how to do them from a conceptual standpoint in the PowerPoint lecture video. We've walked through how to do them in Excel, and now we're going to talk about how to do them in SPSS. And this will provide you with another thing that you can build on, develop from, and in many ways SPSS is a little more user-friendly maybe than Excel, but on some level that user-friendliness can become a problem later on because you forget conceptually what are we doing, why are we doing it, where did the number come from, what does the number mean. So what I would encourage you is every time you use SPSS, at least the first few times, do it in Excel, do it in SPSS, and then look at the output in SPSS. And one, is it consistent with your Excel output? And two, what do the numbers mean? What do the labels mean? Connect the labels in SPSS with the terminology that we're using in the lectures and some of the abbreviations that we've used in the formula sheet and in Excel, because you don't want to have this output, you get it really easily, but potentially it's wrong because sometimes ease does not mean correct. So sometimes SPSS is deceptive. You click some buttons, it gives you output, you think, well, that must be right. And sometimes it's not. You've done the test incorrectly, you've done the wrong test altogether. Those types of things can happen. But if you're making connections with, okay, I know how to do it in Excel, I know conceptually certain things should be 0, certain things should be 1, those things are given. Well, are we getting data output that is consistent with what we were expecting? So we have the SAT data here in this first column. All I've done is copy and pasted the data into SPSS from Excel. In a later video, I'll show you how to actually open data from Excel into SPSS. If you click down in the bottom, so you'll see two tabs down here, data view, which is the view that we're currently in, and then the other view is variable view. And here you can change things like the variable name. So if I wanted to note that not only is this SAT, it's actually the math subscale, I could put SAT math. You can specify the type of data. If you import it, it will automatically assume the type, but you can also adjust that here. We have numeric data, but sometimes when you run into problems, it's because you accidentally have some type of string. And by string, what I mean is there's letters, there's characters other than numbers, and it picks up on some letter somewhere. Maybe whenever you import the data, for instance, instead of having math SAT up here, you include it in the data when you import it. So if you're looking in Excel, you copied everything, including the very first row. Well, then it picks up on that and it will try to make it a string because not everything is a number. You can then, of course, if that does happen, you can click in here, click clear, it will delete that row, and then you can go in, change this to be a number because everything would be numeric at that point. The width is the number of digits. We really only need like 3, but we're going to leave it with 8. You can specify the number of decimal places. With SAT scores, they go on whole intervals. They were originally whole numbers, and so because of that, we don't need any decimal places, but if you wanted to, you could put those there. You can also relabel this. So SAT math, I've put an underscore because SPSS really doesn't like spaces. But I can put a label here, SAT math, something like that with spaces, and it will allow it as a label. It just won't allow it as a variable name. And that can just make your output a little bit clearer, a little bit cleaner, because sometimes rather than putting an underscore, I'll do something like SAT math, run it all together to avoid that space being in there, to avoid an actual space. Personally, since SAT is capitalized and I capitalize the M, an underscore to me is a little bit easier to read, but I can make a clearer, more easy to read label here, and there I can do pretty much anything I want. With values, this is particularly useful if you're working with a categorical variable. For us right now, we're working with a continuous variable, SAT scores, but if we were working with a categorical variable where one, for instance, was man or min, right? I could add in labels to help me better understand what do the numbers mean in the data view. For the moment though, we don't need that because we're working with a continuous variable. And then the last thing that we're going to talk about right now is the measure. So like I said, SPSS doesn't always use the same terminology that our textbook uses, that I use. It's unfortunate. Nobody else calls the scale of measurement scale. Everybody calls it nominal or ordinal or maybe continuous. Nobody else calls it this. However, SPSS calls it scale. So scale is continuous. Scale is the combination of interval and ratio data. Now, ordinal is labeled ordinal, nominal is labeled nominal. Why they decided to call it scale, I'm not entirely sure. I'm sure there's a history behind it. I have never been motivated to go look it up. But now we have all of that. So our data is set up. We could run a graph. So I like to use the legacy dialog. You can use the other ones if you want. I find it faster because the legacy dialog, I am a legacy at this point. Unfortunately, I'm getting to that age. You can go down, go to histogram, and tell it what variable you're going to do the histogram with. So in this case, we're doing it with SAT Math. I'm going to ask it to display the normal curve. What that will do is superimpose a normal curve over the histogram. It allows me to a little more quickly, easily go, is this a normal distribution? Do the data seem to be normally distributed? I'm going to click OK. And then an output window opens up. And looking at the data, it's not perfectly normal, but it's kind of getting there. You know, this is kind of quirky, this is kind of flat over here, but it's got a generally normal shape. As I've mentioned before, I really could also quantitatively check skewness, kurtosis, those types of things. And if I go under Analyze, I can go down to Descriptive Statistics, and I can ask for frequencies. And I'm going to say that I want the frequencies for SAT. I don't actually want a frequency table with them, so I'm going to turn that off. I'm going to unclick this box down here. Under statistics though, I can ask for the mean, I can ask for median, mode, I can ask for standard deviation, variance, min, max. I can even ask for the standard error of the mean and skewness and kurtosis. I'm going to ask for all of them. On some level, you're going to suddenly be like, why did we do this in Excel? Again, it's quick, it's easy, but if you don't know what you're looking for, if you make a mistake, if you enter the data incorrectly, if something is nonsensical, you won't really know it. And so by doing it first in Excel and then building on those skills, building on that knowledge base that you learn from doing it in Excel and basically having to do each step individually, it makes it a little bit easier. And it allows us to more easily tie to your existing knowledge when you look at some of this output, because it is so easy to click so many boxes. Sometimes SPSS output can be a little overwhelming because there's just so many things in it. And so by doing it step by step and then connecting your knowledge to the output, it makes the output a little bit easier to read so that you don't get overwhelmed by the sheer size of the output. We could click charts, and you could do a histogram this way as well. In fact, we'll ask for it. So that way you don't have to do it as a separate step all the time. And then we're going to click OK. Again, our output window will open. So now I see the histogram that I made before. I can't always delete that. I could like click over here, and I could then cut that. I can also open a new output if I don't want my output to stack. So sometimes you're doing a set of analyses, you move to the next set of analyses, you want to save your output and then move forward with it. So here we can see that we have an N of 100. And I'm going to make this a little bit larger just to make sure that you can read it easily. So we have an N of 100. None of the data is missing. The mean is 532. That is consistent with what we saw before. Standard error of the mean is 2.116. You could then go back, and I do encourage you the first few times you use it, Go back to your Excel, make sure this is consistent with what you're seeing there. Median's 529. The mode is 523, so that's the most frequently or most commonly occurring score. Standard deviation is 21.158. We have variance, and then importantly, we have skewness and kurtosis down here at the end. We also see our min and our max. So the lowest score was 489, highest score was 590. If we had asked for the range, we should see that 590 minus 489, so that should be 101, I guess, would give us a range. So it should be that that's equal to our range if we take the min and subtract it from the max. For skewness and kurtosis, these raw scores actually don't give us everything that we need. So I'm going to copy this, and then I'm going to open Excel. Because like when we do a t-test, like when we do a z-test, it's not just about the outcome, right? It's not just about the effect. It's about the effect relative to the variability. So similarly, it's not just about skewness. It's about skewness relative to the standard error of skewness. So what we're going to do is create a ratio, often called a critical ratio, where we say, all right, take this skewness measure, divide it by the standard error in skewness. Similarly, take this kurtosis measure, divide it by the standard error of kurtosis. Importantly, what we see is neither one of those is close to 2. So if you think about the z distribution, which is very similar, we take the effect and then we divide by the standard error. Here we do the same thing. Well, within a 2-tell test with alpha 0.05, our cutoff is plus or minus 1.96. This is really a rough estimate to double check that we don't have too much skewness, too much kurtosis, that our data is relatively normal, and so it is not skewed in one way or another. And there's another video where we talk conceptually about what is skewness, what is kurtosis, what does it look like. You can also look at the book and see descriptions there, where the scores, if they are skewed, there are a bunch of scores that may be on the high end or the low end. We have maybe an outlier, something like that. Kurtosis is where we can have it be platykurtic, where it's relatively flat, so we don't see a normal distribution. There's not as many scores in the middle of the distribution as there should be. And then the opposite of that is leptokurtic, where there's a bunch of scores at the middle, and they're kind of tightly packed around that mean. And so because of that, it violates the assumptions of normality. Here, though, we have a score of 1.14 if we're rounding, negative 0.2262. Neither one of those is close to 2, either positive 2 or negative 2. Because of that, we can, again, feel pretty confident that we haven't violated that assumption of normality. So we have those statistics. We have another histogram. This is identical to the one we saw before. Just shows you another quicker, easier way to maybe get it if you're already running some of these descriptive statistics. All right, so now we're familiar with our data. We've done some descriptives. We double-checked that assumption of normality. Now we're ready to analyze the data. And in fact, for the purposes of this class, most everything we do will either be under Analyze or Graph. So if you're doing a visual, you can find most of them here. If you're running data, you can find it under Analyze. And under Compare Means, we're going to see the one sample t-test, independent t-test, paired samples t-test, and the one-way ANOVA. So most of our comparative tests are Analyze, Compare Means. We're then going to go down to one sample t-test because that's what we're working with today. Our variable that we're interested in is SAT Math. Importantly, the test value. It's not really intuitive, but by test value, what we mean is the population value. So sometimes we don't just do these tests with a population value, we can also do the test with an expected population value. So if we're doing quality assurance work, where we're supposed to have this bike rim, that bike rim is supposed to be 15 inches, we're double checking statistically, are the bike rims 15 inches, give or take, right? Well, we could put in the test value of 15 there. In our case, the population value was 528, so that's coming from the Excel example that we did, coming from the lecture where we provided that information. It was included in the research question or the vignette. Under options, if we have something other than alpha is 95 or 0.05, we can change the confidence interval here. So for our confidence interval, it's going to be 100 minus whatever your alpha level is as a percent. So in our case, our alpha was 0.05. Well, that's basically 5%. And 95 would be 100 minus that 5% gives us a confidence interval. So we're going to click OK because everything's set up correctly. And then make this a little larger just to ensure that you can see it on the video clearly. And you don't necessarily have to make yours larger, but if you are visually impaired, now you've seen how to do that. So we have some descriptives. These match up with what we saw before. We have 100 scores, that's n. We could always change this, modify this to be a small n if we click into it, because really that's for a sample. So maybe a small n would be more appropriate. We have the mean of 532, standard deviation of 21.158. All this is consistent with what we saw before. And so you can see that when you run the one sample t-test, it does in fact provide some descriptive statistics along with the formal inferential statistics. So here, under one sample t-test, we see that test value. I could again change this so that instead of test value, it says population mean, and we could even put mu. If you start trying to actually add the Greek letters, it gets a little bit trickier, but you could put that in there as a reminder that where is that value coming from. If you ever see 0 there, you've probably done it incorrectly, unless it happens to be that the population value on something is 0. But that's the default setting. It rarely is. I don't know that I ever give you an example where that's the right value. And so because of that, if you see a 0 here, you need to go back, rerun this, and put that population mean or the test value if we're doing quality assurance work. And I don't use those examples typically, but you could put that there. This is our T obtain. Like I said, you could write yourself a reminder. So that you can make those connections between the terminology that we've been using and this. Degrees of freedom, DF, is the abbreviation. SIG, two-tailed, that is your p-value. So again, nobody else calls it SIG. I mean, I guess you could call it the significance value, but nobody else calls it that. Why they do, I'm not entirely sure. We see that this is a two-tailed p-value. The reason that's important is we didn't do a two-tailed test. We did a one-tailed test. It's kind of problematic. To convert this, what we can do is take that two-tailed value and divide it by 2. So again, should have left Excel open. While that opens, I'm going to click in here, copy this value. And the way I remember it mnemonically whenever I first was doing this is if I take the two-tailed p-value and divide by 2, I get the one-tailed value. Well, 2 divided by 2 is 1. And similarly, if I take the one-tailed p-value, multiply it by 2, I get the two-tailed value. Well, 1 times 2 is 2. So that's the way that I remembered it. But we're going to take that, and this is our two-tailed value. We are then going to say equals this, divide by 2, and that gives us our one-tailed value. So now we can more specifically, it's not just that p is less than 0.05, that also is true. It is more specifically that p is equal to 0.03. And typically there, we would only report 2 decimal places. The only time you report more than that is if you're saying p is less than 0.001, which is typically the lowest significance that we report. So we could more specifically say p equals 0.03, and we could change then our reporting instead of saying p less than 0.05, which is what you saw in the lecture video. The difference, the mean difference was 4. Again, that's your effect size. So this mean 532 minus mu 528, that's where that's coming from. We reported the confidence interval for this sample mean. You can also report the confidence interval for the difference. So we can do a confidence interval around this mean difference of 4. Because it was a two-tailed test, you see that the lower limit and the upper limit include 0. If 0 is between the lower limit and the upper limit, that would suggest that no difference, right? A difference of 0, no difference, is possible within our sampling distribution. Well, we didn't really do a two-tailed test. We did a one-tailed test. So on some level, this confidence interval doesn't match up with the fact that we wanted a one-tailed test. Unfortunately, in SPSS, you can't quickly, easily adjust that. And so you just have to keep in mind why that might be slightly biased or why that might be a slight error, and then make sure that you, when reporting, report the confidence interval that's appropriate for whether you did a one-tailed or a two-tailed test. That gives you an introduction to how to do a one-sample t-test in SPSS, and if you wanted to then save it, you can save your data, just save as. If, however, you want to save the output, you can go into your output window and you can export this as a PDF, for instance. So if you save it, you have to have SPSS to access it. However, if you export it, you can export it as a Word document, you can export it as a PDF, PowerPoint. There's a number of options there. And then tell it where you want to save it. I'm going to save it on my desktop, and I can put the file name in. So let's say one sample t-test example, and then I can save it as a PDF. It will take a moment to write out once you do that. And at the bottom of my screen, you can't see where it actually says to save it, but if I click on it, it will start the export process. And so I just hit enter because I couldn't access the tab because my screen's a little enlarged so you can read it more easily. So it'll export that PDF and then you'll be able to access it. And that allows you, if you want to work on the homework or something from home, you can do it that way. And so this shows everything. Feel free to shoot me some questions on the discussion boards or via email if you need any additional information about how to use SPSS. And I look forward to talking to you more over the course of the next few videos.